Welcome back. The second talk in this section will be from FSA award uh, recipient, Professor Lei from Indiana University, Bloomington. He's going to tell us about the Monge-Ampere eigenvalue problem and the global smoothness of eigenfunctions.
Thank you very much for the introduction. I would like to thank the organizers for the invitation and for organizing a wonderful conference. So today I will talk about the eigenvalue problem for the Monge-Ampere operator and the global smoothness of the eigenfunction. So I will briefly introduce the eigenvalue problem for the Monge-Ampere operator. Then I will talk about the global Sauder estimate for degenerate Monge-Ampere equation and then how they are applied to the global smoothness of the Monge-Ampere eigenfunction. And if time permits, I will talk about some subsequent developments. So let's recall the classical theory of the vector theory of the Laplace operator. So if we are on a smooth domain omega in Rn, and you consider the Laplace operator, then we have a sequence of eigenvalue for this eigenvalue problem with zero boundary condition. And the corresponding non-trivial eigenfunction are smooth up to the boundary. So that's the classical fact. And in this talk, I will use the D for the derivative. So this is the standard notation, and so this square Q stands for the Hessian matrix. And so starting from the Laplace operator, we have many nice properties of the eigenvalues and eigenfunction. We would like to see what can be done if we replace the Laplace operator by some other operator of the Hessian matrix. And so we know that the Laplace operator is exactly the sum of the eigenvalue of the Hessian. So is it reasonable to replace the sum by some other elementary symmetric polynomials? And so this is, if we just multiply k of them together and add up, that's how the k has an operator. But I will just mention very briefly about the operator later on. But for the moment, I will be concerned with the k when k is exactly n. And that's the last number you can put in this sum here. And so in that case, that's exactly the product of the eigenvalues of the Hessian, which is exactly the determinant of the Hessian. And so one reasonable replacement for the Laplace operator is this kind of Monge-Ampere operator. However, the scaling is different because if you multiply u by the factor alpha, it scales differently. So if we want to have the linear scaling like the Laplace operator, the reasonable object is to raise everything to the power 1 over n. All right. On the other hand, the Laplace operator is elliptic. But the Monge-Ampere operator is not always elliptic because if we look at the linearized operators, it's not always positive definite in the coefficient. And so therefore, we have to restrict ourselves to the class of functions that make the Monge-Ampere operator to be elliptic. And that's the case that the Hessian metric is positive definite. So that's the way we require the function u to be convex. So therefore, if we would like to do the same game as the spectral theory for the Laplace operator, for the Monge-Ampere operator, we need the function involved to be convex. And so let me state the Monge-Ampere eigenvalue problem. Suppose we are given a domain omega, which is bounded and convex in Rn, and we need to find a number lambda and a non-zero convex function u solving this eigenvalue problem. And so, first of all, the domain omega must be convex because it is actually the sublevel set of the convex function u. So this is essential. And on the other hand, because u is zero on the boundary and convex, so in the interior it's a negative, and so therefore the right hand side here can be written as lambda times the absolute value of u. Because u is convex, the left hand side is actually positive, and so therefore you see that we compare the both sides, we see that lambda may be positive. So therefore, we can reformulate the Monge-Ampere eigenvalue problem as follows. So we need to find a positive number lambda and a non-zero convex function u solving this Monge-Ampere eigenvalue problem. Any questions so far? All right. And so if we look at this problem, more of the talks will be about the smooth uniformly convex domain omega n. I will have one slide about the case when omega is general convex domain. But most of the time it's smooth, uniformly convex. All right, so in contrast to the case of the Laplace operator, the Monge-Ampere operator has only one eigenvalue. And that's what proved by Lions about 40 years ago. He showed us their unit number, lambda, depends on domain omega, and a unit non-zero convex function u solving this Monge-Ampere eigenvalue problem. And so because both sides of this equation scale linearly, so the uniqueness of the non-zero convex function u must be understood up to multiplicative constant. That's one fact. And the number lambda here is called the Monge-Ampere eigenvalue of the domain omega. And the function u are called the Monge-Ampere eigenfunction of the domain omega. Regarding the smoothness, as we saw for the Laplace operator, the eigenfunctions are smooth up to the boundary if the domain is smooth. But for the Monge-Ampere eigenfunctions, Lions showed that they are smooth in the interior, but only C11 up to the boundary. So that was about 40 years ago. So C11 here means that if you take the Hessian is bounded up to the boundary. All right. And you may wonder why we have only one eigenfunction and one eigenvalue for the Monge-Ampere operators, because if we consider the simplicity in one dimension, the Laplace operator and the Monge-Ampere operator are the same. However, if we solve the Monge-Ampere eigenvalue problem in one dimension, so it's exactly the classical problem, and so we see we can calculate explicitly all the eigenvalues, all the eigenfunctions, but we can only choose the first eigenfunction to have the sign to be convex. All the other eigenfunctions we have concave part and convex parts. And so when we restrict the convexity on the solution, that impose a lot of restriction and it impose the uniqueness. So that's the idea. All right. So later on, when we do not have to worry much about the exact value of lambda, we can always rescale lambda to be 1, because the reason is that if we rescale the domain omega by the factor t, this is the way we scale the Monge-Ampere eigenvalue. So sometimes I just take lambda to be 1 if we don't have to worry much about it. Okay. All right, so let me mention very briefly how to construct the Monge-Ampere eigenvalue. So Lions showed us lambda can be computed as the supremum of all number t, which is a negative, such that this Monge-Ampere equation has a C2 solution up to the boundary. And so the way to think about this is that look at the k when t equals 0, and on the right hand side here, we have number 1, but the domain omega is smooth and uniformly convex, so therefore the existence of U0 is clear. And once you have the existence of U0, then we look at the linearized operator concerning U0, and we see that it's uniformly elliptic with continuous coefficient, and we can use some kind of implicit function theorem to go further from 0 to something further. And so therefore, we can go a little bit more. And then there's some comparison principle to show that actually you could not go all the way up to infinity. So you have to stop somewhere. And so that's the lambda will be finite. And when you approach t to go to the value of lambda, the infinity norm of ut of this Monge-Ampere equation go to infinity. And if you rescale it to have the infinity norm to be 1, then actually this quantity converts to the solution of the Monge-Ampere eigenvalue problem. So that's the way to construct in the BD way the Monge-Ampere eigenvalues and the Monge-Ampere eigenfunction. So the next slide will not be related to what I'm going to say later on, but somehow I would like to showcase the fact that many properties of the Laplace eigenvalue eigenfunction carry over to the case of the Monge-Ampere operator. So including the Fourier characterization of the Monge-Ampere eigenvalue. Because if we recall that for the first eigenvalue of the Laplace operator, we can find this at the infimum of the Rayleigh quotient. But somehow the way we write it in the classical books, we don't see the Laplace operator, so it may be difficult to generalize to the case of the Monge-Ampere eigenvalue problem. So one way to do that is that in PDE, when you got stuck, you just do integration by part. And so in this case, we integrate by part, we can see the Laplace operator appears in the expression. And so when we see the Laplace operator, maybe there's some hope to do for the case of the Monge-Ampere eigenvalues, and that's how show this for the Monge-Ampere eigenvalue. So he showed us when you raise the Monge-Ampere eigenvalue to the power n, it's the infimum of the expression. And so this is the expression involving candidates U which are convex in the domain, 0 on the boundary, and lifts it up to the boundary. And you see that the expression in the numerator is very similar to the expression above here. But at the denominator, it's a little bit different because the way we scale. So we see that the homogeneity of the numerator is n plus 1. And so therefore, the power here is n plus 1. So that's we want to have the same homogeneity. All right, so this is the way we characterize the Monge-Ampere eigenvalue variationally. And this formula can be extended to the case of the K-Hessian operator by a paper by Quang in IU Math Journal. So the way I put it, because this is where I come from. That's the journal in my department. All right. So now we saw many interesting properties of the Monge-Ampere eigenvalues and eigenfunction. But now the question is, what about the global smoothness? Because for the Laplace operator, we have the global smoothness of the eigenfunction. What about the global smoothness of the Monge-Ampere eigenfunction? And so the global smoothness of the Monge-Ampere eigenfunction were first asked by Schrödinger about 40 years ago. And it turns out to be a difficult problem because somehow for the Monge-Ampere equation, a lot of facts were known for the right-hand side to be strictly away from 0. And so that's the case when you prove the global C2 estimate, you look at the linear operator becomes uniformly elliptic with C alpha coefficient, and you can do further analysis. But in this case, the right-hand side going to 0 when you're approaching the boundary. So that's the key difficulties of the problem. And so that's called the degeneracy of the right-hand side because it's going to 0. And so this is the quote that from the seminar book by Figari. So that's just what I just said in a few minutes ago. Okay. So now I would like to mention about the history of solving this problem. What's the solution? So we saw before that Lions in his result, he proved the interior smoothness, and then regarding global smoothness, he proved C11. And then about 15 years ago, Quang and Quang proved global smoothness of the eigenfunction in 2 dimensions. And so that technique was purely 2-dimensional. And then there was a big result by Savin a few years later. He improved the result of Lions from C11 to C2. So although it looked like you improve the Hessian from being bounded to being continuous, but that's a very important result because it lays out a lot of ingredients and arguments for later work. So I will mention briefly his result later on, but I will not say how to prove it. It's quite involved and delicate. And so later on, in a few years later, together with Savin, we were able to prove that in all dimensions, the Monge-Ampere eigenfunctions are globally smooth. And so this is the result that I would like to mention briefly how to prove it in a couple of minutes later. Are there any questions so far? All right. So before doing that, I will mention briefly the result in the case of the Monge-Ampere equation, where we would like to prove the boundary C2 alpha estimates. As I mentioned before, in order to study the higher order regularity for this non-degenerate equation, the critical estimate we need is the global C2 alpha, because when we have the global C2 alpha, we look at the linear operator that become uniformly elliptic, and we can use the classical Sauder theory. And so the C2 alpha is the critical case. There was a lot of work spanning over the last 40 years. The final result was given in a precise way by the work of Savin, where if we would like to have the boundary C2 alpha estimates, somehow we only need F to be C alpha. But all the work before, Either we need more condition on F, like F is C2 alpha or C2, or we need the global condition on F. Somehow the result of Savin indicate that we don't need actually the global C alpha to get certain kind of C2 alpha estimate. What he needs was some kind of bond-wide C alpha. Bond-wide C alphas allow you to do the Taylor expansion around one point. If you can do the Taylor expansion around one point on the boundary, then you can do the Taylor expansion for the solution around that point up to second order. And so that's the meaning of this bond-wide estimate. I will give you a more precise definition of the bond-wide C2 alpha later on, but somehow this result here, you don't need the global C alpha of F to get some kind of C2 alpha estimate for the solution. All right, so somehow related to Monge-Ampere eigenfunction are the degenerate case where you allow F to vanish somewhere. And so in that case, without a lot of structural condition on F, the optimal result were obtained by Quang, and Quang, where they show that if certain power of F is C11 up to the boundary, then the solution is C11. Okay, then of course this is optimal in the sense that you have this integrability, but you don't need further structural condition on the right hand side F. Okay, so now coming back to our Monge-Ampere eigenvalue problem, we would like to understand how degenerate our solution is. So somehow in this equation you can always normalize the solution U to we have norm 1 because it's scaled the same way both sides. And then by a very simple argument using comparison and convexity, we can show that the solution U is comparable to the distance to the boundary. And so therefore, if we come back to our equation on the right-hand side, we see that the right-hand side is comparable to certain power of the distance to the boundary. In this case, the power alpha is exactly n. But many analysis carry over to the case alpha is positive. So that's the way, instead of using n, I will just use the general number alpha in many results later on. And so somehow, on the other hand, because the domain is uniformly convex, that if you subtract a tangent hyperplane, then the resulting function will grow quadratically away from that point. And so this condition is very crucial for many analysis later on. And on the other hand, one we have that we know that the solution U is globally C1 up to the boundary. Then if you divide by the distance function to the power alpha here, alpha is for n, then what will remain will be a globally smooth, globally elliptic function. And so this is another condition. So somehow we have the degenerate Monge-Ampere equation where the right-hand side F is comparable to certain power of the distance to the boundary. And then if you divide F to this power, then you have a globally smooth, globally elliptic function. All right, so as we saw before, the result of Lions allow us to conclude that U is globally C11. And so now, how to obtain global C2 alpha, and how to go from global C2 alpha to C infinity. So as I mentioned, step 2 is usually very, very easy in the case when the right-hand side here is bounded away from 0, because in the classical Sauder theory, when we had global C2 alpha, you can bootstrap. But in this case, because the right-hand side is degenerate, you could not do that easily. And so step 2 is non-trivial. All right, so recall that our equation is of this form. And so we would like to understand what can be done in this situation. And so before going to the analysis, I would like to mention a very simple case, but that gives you the idea how to play with the numerologies and what happens in the scaling. So the simplest case of the equation where the right-hand side is comparable to the distance to the boundary is this equation in the upper half space. Although our equation is on the uniformly convex domain, but let's say that in the this imaginable world, our equation become on the upper half space. And so this is the equation. And so on the upper half space, so So this is the way that I write Rn. So the first I minus 1 coordinate I put into x prime, and the last coordinate as n. And so this is upper half space. And of course, we also saw that our Monge-Ampere eigenfunction separate quadratically away from its tangent hyperplane on the boundary. And so this is the way that an illustrative example of that situation. And so if we look at this equation, then you see that clearly there are many solutions. One solution is this, which is not polynomial, even if when alpha is an integer, because there's a factor over here. But the one that is very useful to us is u0, so I will mention what is u0 here. And so if we look at this equation, there are at least two invariances. One is the translation invariant. So if we translate coordinate by this way, so we just keep Sn intact, but we just slide the first I minus 1 coordinates by some vector tau prime times Sn. So tau prime is vector in I minus 1. Then if we slide the coordinates, then we still have the same solution. And then on the other hand, if U is a solution, we rescale U tilde by this formula, then we also have the same, the function U tilde also satisfy this equation. And so the way we rescale, we use the R5 map FH. And we see that in the first I minus 1 coordinate are homogeneous, and we scale by the factor n to the power 1/2. But the last coordinate, we scale differently from the first I minus 1 coordinates. And so we have the different scaling. So I will mention what is the implication of the different scaling in different coordinates later on. So there's one solution that is very helpful to us, and it will be helpful to in the many problems in BD is that this solution is self-invariant or self-similar, because somehow if you rescale this way, then you get back to the original function. And so this function will play an important role in our analysis later on. All right, and so this is the formal definition of the C2 and bond-wide C2 and bond-wide C2 beta. So the bond-wide concept will allow you to do the Taylor expansion with control error. That's the idea. And so we say that the function U is C2 at the point x0 if there's a quadratic polynomial Q, such that if you subtract Q from U, you have this error. And the error is little o of the distance from x to the point x0. And on the other hand, if you would like to have the C2 beta, the bond-wide C2 beta, then there should be a polynomial, the quadratic polynomial Q x0, so that if you subtract Q x0 from U, you have this error. And so here, you only need the capital O, big O. Because here, if you replace little o by big O, then you only have bond-wide C11. But bond-wide C2, you need to have a little o. All right, so now let's come back to our degenerate Monge-Ampere equation. So this is the equation that I mentioned earlier. So the right-hand side is comparable to the distance to the boundary. And so the ratio I put to be G. And so in this case, we are working on the upper half space. So let me mention, this is not exactly the, so we can always put our convex domain into the upper half space. That is tangent to the origin, to the Sn equals 0 at the origin, and we also assume that the boundary to be C11. And then the function g here, we only need to be continuous at 0. We don't have to worry about far away. And at the origin, g is positive. So the important result of Savin allow us to obtain the bond-wide C2 estimates for this equation at the origin, if we just have very natural condition on the boundary. And so what the theorem said that if we look at this Monge-Ampere equation and you subtract the tangent hyperplane to the graph of U at the origin, so this is that, and what is left is the boundary data phi. And so if you assume that the boundary data phi is C2 at the origin, and the solution U separate quadratically away from the origin, then the conclusion is that the solution U is C2 at the origin. And C2 here just bond-wide C2. However, his result is much stronger. So his result said that there are sliding after you slide, then because this is the invariant of the equation, you can subtract you can do the Taylor expansion. And so this is like the usual Taylor expansion, and this is the error that you get. But somehow Q naught here is the quadratic part of the boundary. And you also need some part of Sn because that corresponds to the power d alpha. But somehow if you look at the way the errors enter into the analysis, it's much stronger than the error we usually see, because usually in the C2, bondwise C2, this one's supposed to be only Sn to the Sn square. But in this case, it's Sn to the power 2 plus alpha, where here alpha is positive. So when you are close to origin, so this is a much smaller error. And so actually, this is not only about the C2, bondwise C2 estimate, but it's the C2 estimate with respect to the degenerate matrix. So this is the degenerate matrix of the equation. And so this is a much stronger result than the C2 estimate for the Euclidean matrix. And so somehow this is the degenerate matrix that will enter in our analysis later on. And so you see that this is a very strong result. So somehow other dimensions, so this is I just said before, so this map called slidings along the Sn equals 0. All right, so once we have the C2 estimate, we want to go to the next order. What can we get? Can we get 3, or can we get something else? So if we look at the model, the example that we just wrote down, then this typical equation had a self-similar solution, which is given here. And somehow, if we look at the ways all the coordinates are scaled, we say that all the coordinates S1, S2, to the n-1 has degree 1. So that's our convention. Then because of the scaling of S and the difference, so somehow when we say that all the Si had degree 1, then Sn must have degree 2 over 2 plus alpha because of this formula. And so somehow we saw in the result Savin in the C2 estimates that we can, when we do the Taylor expansion, this is what we saw. Of course, this I put the comparative, so there's some constant floating around, but they're positive. And so what is the next polynomial if we want to do the higher order estimate? So somehow in the classical case, when we go from, when we have C2, then maybe the next polynomial is the third order polynomial. And so this is something like this. However, because the degrees of Sn is only 2 over 2 plus alpha, then actually this polynomial does not have degree 3. It only have this degree. And so it's much smaller than 3 when alpha is large. Because in the Monge-Ampere eigenfunction, the alpha here is exactly the dimension. And so therefore, we see that if we want to go further in the Sauder estimate or in the higher order derivative estimate, we could not get more than 2 over 2 plus alpha in this step. So this is the example, the situation we see. Okay. It turns out that exactly the case that we did. So we can get exactly this number of derivative at the next step when we do the Sauder estimate. Okay. So, all right. So there's this slide a little bit technical, but let me try to explain. Okay, we have the same setting as in the bondwise C2 estimate. Now somehow we would like to do the higher order derivative estimates, and so we want to do the C2 beta. And so beta is smaller than this critical number. So this is the number we just saw before. So that's the net level of derivative that we can get. And we assume that the boundary data of the solution here is C2 beta at the origin. And the solution also separates quadratically away from 0. And now we assume that the ratio function G is C gamma at the origin. So when I do not say anything, C gamma means C gamma with respect to the Euclidean matrix. But however, if we come back to the case of the degenerate matrix, there's a way to transfer the C gamma in Euclidean to the degenerate matrix. So that's actually this relation between gamma and beta allow you to say that actually G here is now C beta with respect to the degenerate matrix. And so this is just a simple relation. And so somehow with all the information, then When you have the boundary data is C2 beta, then the solution to this Monge-Ampere equation is actually C2 beta at the origin. So it means that we can do the Taylor expansion and we can have the control error. And this is not only the C2 beta estimate with respect to the Euclid metric, but it's also the C2 beta estimate with respect to the degenerate metric, because this is the power enter into the error term. All right, so somehow let me say about how to prove the point-wise C2 beta estimate. It's a little bit technical, but somehow here how it goes. Our domain is uniformly convex, but somehow using the point-wise C2 estimate, we can try to rescale the function u and the domain so that the new function is well approximated by the particular solution u naught on the upper half space. And now when we scale the domain becomes flatter and flatter and flatter, and so somehow it becomes very flat. And so in the end, when we use the C2 estimate, we can put ourselves in the situation that everything is a small perturbation of the solution U naught on the upper half space. So that's the main message. And so somehow, therefore, when we are in that situation, we can assume that the solution U is a small perturbation, let's say of order epsilon of the solution U naught, and the ratio function G is 1, and the boundary data is just this quadratic polynomial in the S prime, and then the boundary near 0 is just the hyperplane at equals 0. And so how to go further? So we need to prove the C2 beta estimate. So the way to do that is that if you focus in a small region around the origin, you rescale using the alpha map FH, which is the scaling invariant map of the equation. Then somehow if you focus on a smaller and smaller region around the origin, you improve the error from epsilon to some smaller factor. And the smaller factor that there's some factor called theta naught playing around. So somehow I call the height, but somehow, so this is a little bit technical, but here how it goes. So somehow for the first region, you can say the sliding map AH is actually the identity map. Somehow so then this is the identity, so somehow you rescale exactly like the scaling of the equation. And when you rescale the equation, when you go into a small domain, you improve the error, you start with epsilon into this, by this factor theta to the power beta over 2. So when you do that, you see that everything now, so this is the key lemma. But to prove this lemma, so somehow you do the kind of linear analysis. So in the sense that suppose that you start with u is very close to u naught of all the epsilon. So you look at this ratio, it turns out that this ratio can be shown to be well approximated by the solution of this Crucian time operator. And so this is the operator when if alpha equals 0, this is exactly the Laplace equation. But when alpha is positive, so this comes from the linear operator of this Monge-Ampere equation. All right. And so somehow we saw that this ratio is well approximated by the solution of the Crucian time operator. And on the other hand, the Crucian time operator with the zero boundary condition on the S equals 0, it had the C2 over 2 plus alpha estimate. So this is the critical number that I just showed you a few minutes ago. And so this is exact estimate. All right. So somehow, and then that's it for one fixed scale, and then you can do for many, many scales, and then you obtain the result. So, all right. So that's the result that we only have the C2 beta estimate only at one point. So one point, it means that you can do the Taylor expansion around that point. And so you can do the point-wise estimate for every point on the boundary. But in the interior, this equation, you can always assume that to have the smooth solution in the interior. So therefore, if you want to do some kind of global estimate around one point, you need to talk, to let the interior estimates and the boundary estimate to talk to each other. And so somehow, in the end, we need to use some geometric property of the sublevel set of U near the boundary to obtain the global C2 beta estimate. So let me state the result. So the result said the following: if you have this Monge-Ampere equation when all the boundary data are C2 beta, then somehow beta is in this range, And now we need one condition that beta is not smaller, not bigger than alpha. Then the solution of this Monge-Ampere equation, when it separates quadratically away from the tangent hyperplane, is that the solution is C2 beta for some around some ball of radius delta around the origin. And so this technical condition be arrived because if we want to have C2 beta, then that's very clear from the equation, because if we look at this expansion here, this expansion is the point-wide estimate, but if you want to upgrade to the global estimate, so if you want to have the C2 beta around 1 point, then the beta must not be bigger than alpha. So that's clear from the expansion. All right. All right, so now let me summarize in the simple case that we applicable to the Monge-Ampere eigenfunction. So in the case of Monge-Ampere eigenfunction, we have the boundary 0, and we have the right-hand side to be comparable to the distance to the boundary with the power alpha. And this ratio here is global ellipsis. And so we just, and then let's say that beta is smaller than alpha, then the conclusion is that the solution to this Monge-Ampere equation is actually C2 beta up to the boundary. Then because the case of the Monge-Ampere eigenfunction is the case when alpha here is exactly n, and so therefore this result implies that the Monge-Ampere eigenfunction are actually C2 beta for all beta smaller number. And so somehow we are still far away from C infinity because we only have just C2 beta for some small beta if n is large. And so how to do next? So the next step to improve from the C2 beta estimate to C infinity. As for that, we need two techniques. We need to use the holograph transformation and the Legendre transform. And so first of all, in this equation, you can always rescale lambda to be 1. And then now you can always assume that 0 is on the boundary and the En is the internormal of the boundary. And then you can write down locally near the origin that the boundary is the graph of function phi of n minus 1 variable. And then you do the rotational coordinates. And then when you do that, then the graph of u, the eigenfunction near the origin, can be represented as the graph of some function u tilde in the upper half space. So now you can write out the equation in the upper half space, and so this is the equation in the half space locally. And so everything is doable because we already have the C2 beta estimate. Because for that, we don't get much information about the equation. We can write it, but it's not very useful. And so now, when we have this equation, it turns out that the right-hand side here, this number here is positive. And so it's a very nice term, and we have the equation on the upper half space. And so now I relabel, so instead of u tilde, I call u. Okay, so this, and then now if you look at this equation, so somehow this term is a nice term, so it just involves the derivative u in the Sn direction, but no others. And so therefore, if you take the derivative of this equation in all xk when k smaller than n, you see that it appears nicely in this equation. It does not interfere with this Sn. And so somehow we see that the equation is very nice in a non-degenerate direction, in all directions up to x1 to Sn minus 1, but maybe it has some trouble with Sn direction. And so that's the issue. And so to do that, one way is that you look at the left-hand side. Somehow the left-hand side you can write down, you separate all the highest order derivative in u, and you see that there's one term that involves all the nice second derivative in the non-degenerate direction, and this is the double term. And so somehow we can try to isolate this term. And so the way to do that, this is a nonlinear operator. So therefore, but there's one way to do that. We use the Poisson-Legendre transform. When you use the Poisson-Legendre transform, so you transform u into the function u star, and so somehow it's a kind of Legendre transform on each line as n equals constant. And if you do the transformation back, you see that u star become u. And so therefore, if we want to study the regularity of the equation, we only need to study the regularity of u star. And so this is the equation. And so somehow, if we look at this equation, we see that the separation of the ordinary direction from the bad direction, because all the bad direction is appear with low order term, and this is high order term. And so somehow, you see that because u star always see to beta, and so we look at this equation. So somehow, if we differentiate in all the non-degenerate direction, we have some kind of Gaussian type operator with the C, with the Holder continuous coefficient. And before you saw this kind of equation with this right hand side to be 0, and this term is exactly kind of Laplace in the analytic one direction, but here there's some matrix Aij, but it's uniformly elliptic, but it's nice because we already have the, these come from the second derivative of the solution u star, which is Holder continuous already. But for this equation, so somehow we can prove the global Sauder estimate. We prove the global Sauder estimate. So in this case, usually I put alpha is equal n, but somehow for general discussion, I can just put general alpha here. It's just positive. So somehow for this equation, we can obtain the global Sauder estimate. So we can differentiate the solution in all directions in y prime. But when we do the Sauder estimate, we can only gain two derivatives in the yn direction. And so therefore, at least for all the derivative of yn up to second order, we had a control. But in order to control all the higher order derivative u star in the yn, we look at this equation again, we differentiate the equation in the yn direction. It turns out that all the higher order derivative of u star in yn can be expressed as a combination of some power of yn and the certain derivative of u star in yn with the smaller power, smaller the number of derivatives. And so here the important point is that when alpha is a party integer, actually in the Monge-Ampere eigenfunction is n, then if we differentiate this equation with respect to yn, we don't have any issue with the term yn to the alpha. But when alpha is not an integer, we have some problem because it could go to 0 or go to infinity when we are close to the origin. And so therefore, when we have all control on the u star on all derivative up to second order, but from this relation, we see that we can also have control of u star for all derivative in all direction, in all yn and all direction in y prime. And so from that, we can conclude that u star is actually smooth up to the boundary, and from that, we can see that the Monge-Ampere eigenfunction is actually globally smooth. All right, so we have a few minutes left, so let me mention a few results coming from this. And so the Monge-Ampere eigenvalue problem corresponds to this equation when alpha is equal n, but it's also interesting to study this equation when alpha is not n. And so that's the so prove that for any alpha not equal n, you also have a non-zero convex function u to this equation. And from exactly from the proof of Ovidiu Savin, we can say that when alpha is a party integer, then the solution also see infinity because we can differentiate many times either we have polynomial or we don't have anything. But on the other hand, when alpha is not an integer, then we have trouble because if we look at this expression, we differentiate the expression, then if alpha not integer, then at certain point it becomes negative, and then we go to infinity when yn go to 0. And so therefore, actually, in the follow-up paper, I saw that when alpha not integer, the solution had this number of derivatives, but do not have any more than that. So this is the optimal number of derivatives that solution can get. All right, and so on the other hand, in the recent paper, you see that we already proved the global smoothness of the eigenfunction. So you might wonder what happened if the domain omega A analytics, the boundary analytics. Then the recent result of Quang and show that actually when alpha is part integer, then the solution to this equation is globally analytic. So I would like to mention one work that's in the flavor of the Monge-Ampere eigenfunction. That's the work of the Quang and Yao last year, where instead of having this number here, they replaced by certain expression. This is very related to the Legendre transform, and this problem comes from the Galabi-Yau matrices. And so somehow, if we look at this Monge-Ampere type eigenvalue problem, then using the techniques of So and Ovidiu with Savin, Quang and Yao were able to prove the existence of a convex solution to this problem, which are smooth in the interior and C2 beta atoms up to the boundary. And so somehow when alpha minus n both sides scale the same way, that somehow this term you have to put some constant like the Monge-Ampere eigenvalue in the front. But otherwise you can put any number. Okay, so I think my time is up. So I think that I just mentioned one remark that although we see many properties of the Monge-Ampere eigenfunction that's very similar to the case of Laplace operator, even from the variational characterization and global smoothness, but there are very interesting question: what happened to the global smoothness of the K-Hessian eigenfunction when K is between 1 and n? So that's completely open. So I think this is the problem. I would like to advocate that if we can say something about beyond the C11 estimate, like in the case of the Lions result. So Suya Wang already showed that the K-Hessian eigenfunction are globally C11, but it not know whether it's globally smooth because the technique in the Monge-Ampere equation do not apply to this situation. So with that, thank you very much for your attention.
Thank you for the nice talk. So any questions from the audience?
That counterexample, C infinity in case alpha is not an integer?
No, that is not a counterexample. It's a basic fact. I can show you why it does not work. So that's not a counterexample. It's obviously not because okay. So I can show you why it's not smooth. Okay, so so this is the result, right? Okay, so can I have some blackboard? I think I can give job, please. Okay. So this is a fact, it's not a counterexample. Okay, thank you. Okay. Okay. So can I have the please? Do you have one? Oh yeah, the white one. Thank you. Okay, so if we look at this equation, so let's say that this is u to the alpha, and let's say if u is C3 plus the integer part of alpha up to the boundary, then the left-hand side is actually C1 plus alpha up to the boundary, because we lose two derivatives on the left-hand side. On the other hand, once we have this, you can always write u is the distance to the boundary times times function g, and you lose one derivative, so g is actually C2 plus alpha. And so therefore, if you compare with this one, you see that the right-hand side is exactly the alpha, the distance to the boundary to the power alpha times g to the alpha. And so somehow this term, but it's nice, so somehow if you take the derivative 1 plus alpha time, this term will survive, but this term you are double. And so they don't match. So this is a fact. Yeah. Thank you for your question.
Any other question? Okay, so maybe let's thank the speaker again.